Next lesson in Chem 1 on solutions, in which we're going to take a look at using molarity calculations in solution stoichiometry. Some of you will be happy to know that this is going to be our last new introduction to stoichiometry, because this is going to be our last way of actually finding moles. Although this stoichiometry, if we do get to acids and bases, this stoichiometry will come back. So it's not going to be the end of stoichiometry, just the end of the new stoichiometry. So one of the things that I've been trying to emphasize, and I hope you've been picking up on, is that whenever we do stoichiometry, we want to have some way of getting from whatever unit, I thought I picked the green pen, whatever unit we start in, to getting to moles of that given. So mole unit of that given to moles of the given. And we saw this with gases, in which we had to go from the volume of the gas to get to the moles of that compound. We saw this with molar mass. And so now we're going to use the volume of a solution as the starting or ending point in our calculations. All right, so we're going to remember that molarity connects the moles to volume. So it's a conversion factor between moles and volume, just like molar mass is a conversion factor between moles and mass. And so molarity is moles, moles divided by liters. I'm not sure why that's coming up green. And so we can remember that we can use that as moles over liters, or as we've seen before, we can use 1 over molarity as liters over moles if we need to use it as the reverse. So let's fill in the blanks here. Molarity is the conversion factor between moles and volume. And let's get right into a problem that's a volume to volume to problem, where I've got 2 different volumes of 2 different solutions, most likely at different concentrations, because it's going to be rare to find concentrations that are going to be the same unless it's really set up that way. So we're not going to do any of those. And we're going to start with the volume of our given and convert to the moles of our given. And then we're going to use our mole to mole ratio from the balanced chemical equation, so moles over moles, to give us the moles of the wanted, and then finally the volume of the wanted. Now, I do have a few balancing problems for you on the worksheet. This is just to keep that fresh in your mind. And this is a pretty easy one if you remember the balancing. Start with the most complicated compound. We have the Fe2 and SO43, so the iron 3 sulfate. We're going to put a 2 in front of the iron 3 chloride. We're going to put a 3 in front of the potassium sulfate to balance those 2 compounds. That's going to give us a total of 6 potassiums and 6 chlorides, and so we're going to need 6 potassium chlorides. All right, so don't sweat these guys too much. The difficult balancing is behind us. So now we want to know what volume in milliliters. Milliliters, that's going to be an important thing in a moment. We're going to have to do some converting. 0.248 molar iron 3 chloride. So this is our wanted. React with 38.9 milliliters of 0.435 molar potassium sulfate. And so this is our given. All right, so we know that to deal with moles, we have to be in liters. And so let's do our conversion first of our given. We have 38.9, the volume of the given. Start with that 38.9 milliliters and multiply by, let's see, we put liters up on top, we put milliliters on the bottom. Milli means 1 times 10 to the minus 3, and a 1 there. And when we do the math, we're going to get 0.0389 liters. Notice it went down. Now, let me show you what I did in class recently to show you how to do this in a slightly less dimensional analysis way. And that is, if I want to take the 38.9 milliliters and I want to go to how many liters that is, remember that I take 1,000 milliliters is 1 liter. And so basically I'm going to keep that ratio the same. I'm going to divide by 1,000, and so I'm going to get 0.0389 liters. And as you can see, as you should expect, the volume went down, or the number went down. The volume's the same, but the number went down. Now that we've got the liters, now we can go into our stoichiometry, and so we want to know how many. I'm going to give myself a lot of room to work here. How many milliliters of FeCl3? And we're going to assume it's the solution here, since we're dealing with the solution. And that's going to equal, let's start with our 0.0389 milliliters, but do throw in the K2SO4. You want to have that because you want to be able to cancel out the moles in a few minutes. We're going to multiply that by, now we've got the molarity of the K2SO4, so we're going to put 0.435, and we're going to split that unit up into moles of K2SO4 divided by 1 liter. Oh, you know what? I put a milliliters there. I should have put liters there. 1 liter of K2SO4. So the K2SO4 liters cancel out. Now, if I stopped here, I would have moles of K2SO4. Just like we had before, we're taking the volume, the 0.389 liters, and we're multiplying it by the molarity, gets at the moles. But we don't want to stop there, so we're going to continue with our calculation, and we're going to see up above that we have 2 moles of FeCl3 and 3 moles of K2SO4. So let's bring those down as our mole to mole ratio. We want the K2SO4 in the denominator, and that's the 3 moles. And so we're going to put the 2 moles of the FeCl3 up on top, cancel out the units of the K2SO4. And now we're going to do our reverse molarity, because, I kind of don't have enough room. I'm going to move that down just a little bit here. So we want to have, in this conversion factor, we want to have liters up on top, and we want to have milliliters, moles down on the bottom. So this is going to be liters of the FeCl3, and we're going to have moles of the FeCl3. So remember, molarity is moles over liters, so we're going to put the molarity, the 0.248 moles of the FeCl3 on the bottom, and the 1 liter up on top. Now, the first thing I'm going to do, and I needed a little room here, so I'm going to come down here. First thing I'm going to do here is do this whole calculation. Moles cancel out, going to give us liters. So let's get liters first. So if we do this whole calculation, we're going to get 0.0455 liters of the FeCl3 solution. But remember, I asked you for milliliters, so I need to convert my answer from liters to milliliters. And so let's just go ahead and do that. How many milliliters? I say, let's go back up here. I should have made this liters up at front at first, because I'm getting my liters first. First the liters, and now we're going to go to milliliters. So how many milliliters of the FeCl3? And that's going to be, take the 0.0455 liters FeCl3. Now remember, 1 liter becomes 1,000 milliliters. So this is going to have to be a bigger number. So when we put our conversion factor here, you could put 1,000 milliliters. You know what? Let's go ahead and do that. Since we know 1,000 milliliters is going on top, we're going to put the milliliters on top. To go 2 milliliters, put the 1 liter in the denominator. The liters cancel out, and we're going to end up with 45.5 milliliters of the FeCl3 solution. So the center part of the stoichiometry is just what you've seen before. Just pay attention to what's the wanted, what's the given, and you should do fine. Now, there is one trick that I'm going to show you here. You don't have to use it, but if you can master this trick, it'll save you a little bit of time. And that is, we can put milliliters into the problem as I call it like an internal conversion factor to avoid having to do the conversions at the beginning and at the end separately and make it a little easier for yourself. So recall that molarity is the number of moles over 1 liter. Now, using this trick will work in stoichiometry, but it's not going to be something you want to do if you're trying to calculate the molarity. Or, and let me get rid of that line, or the molarity can be thought of as the number of moles in 1,000 milliliters. After all, 1 liter and 1,000 milliliters are the same. So the molarity, you can put the M up on top. Here, let me get rid of the number sign. The molarity, the number of moles in 1,000 milliliters. So how that would work in this kind of a calculation is as follows. Instead of having to do the liter to mole liter to milliliter conversion, we're going to just go ahead and start off looking for the milliliters of the FeCl3, as I tried to do up above mistakenly. And we're going to take that 38.9 milliliters of the iron 3 chloride. And now when we use the molarity, we're going to put that 0.435 moles, use moles, not molarity though, of FeCl3 over 1,000 milliliters of the FeCl3. Right? So if there's 0.435 moles of FeCl3 in 1 liter, there's also 0.435 moles in 1,000 milliliters. Now the milliliters will cancel out, and the calculation then is just going to be the same as we saw before. We've got the 2 moles of the I've been saying FeCl3. That should have been K2SO4. My bad. That should be K2SO4 there and there. It's really easy for me to erase, isn't it? Because now we have the 2 moles of the FeCl3 up on top and the 3 moles of the K2SO4 down at the bottom. Milliliters canceled out, moles cancel out. And now on the back side, we're going to do the same thing. We're going to put the 1,000 milliliters of the FeCl3 up on top, and we're going to put the molarity 0.248 moles of FeCl3 on the bottom. And the moles are going to cancel out. And if you're really paying attention here, you can see that those thousands are also going to cancel out with each other. And that's one of the reasons this works well. And so we are going to get directly that 45.5 milliliters of the FeCl3. And go ahead and try that and convince yourself that it does work. So this is what you do when you have a volume-to-volume problem. We start with one molarity, we end with another molarity, we get the volume at the very end. And as I said, notice this only works when converting milliliters to moles, not when you're calculating the molarity. The second kind of stoichiometry problem is going to couple one of these volume to moles or mole to volume problems with a traditional mass to mole or mole to mass problem. So you can have a mole to mass and mass to mole using molar mass, and then volume to mole or mole to volume using molarity. So you can actually go, these should be double arrows because you're going to go one direction or the other. Now, in this particular example, I'm going to start with, here's my given. I'm going to start with the grams of the silver, and I want to know how many milliliters of silver nitrate solution I need to produce to precipitate. This is a single replacement reaction. I'm going to make this silver precipitate, 12.5 grams of silver. I've given you the molarity, so let's start with that molarity. I'm sorry, that's going to be our wanted. So let's start with the grams of this silver. So the wanted is how many milliliters of silver sulfate solution are needed to make 12.5 grams of silver. Now, this should look familiar to you. We've got grams. So to go from grams to moles, I need molar mass. So let's get that molar mass. 1 mole of silver. You can look it up on your periodic table, or I will just spot you for this one, 107.9 grams of silver. And again, this is going to leave me with moles of silver. So now I cancel out the grams. I've got my moles of silver. Now I go to the mole-to-mole ratio, the balanced chemical equation. Notice I've got 2 moles of silver. It looks like in weird moles of silver in the denominator, and I only need 1 mole of silver sulfate in the numerator. Let's cancel out the moles of silver, and now that's going to get me to moles of the silver sulfate. Since I have moles of the silver sulfate, I've got my molarity. There's my molarity. So now I can put that 0.568 moles of the silver sulfate, Ag2SO4 in the denominator, and 1,000, since I want milliliters, 1,000 milliliters of the Ag2SO4. If you wanted liters, you could just put liters there and you'd be good. And if I don't specify, you can pick whichever one you want. The moles cancel out, and we do our zigzag math, that infamous zigzag math from before, and we are going to get 102 milliliters of silver sulfate solution. And again, with all these calculations, I want you to make sure, probably a good idea to pause the video here and go through the calculation. Make sure you're getting the same answer that I'm getting. All right, we're almost there. Turn the page over, or on the next page, we have one last kind of problem involving stoichiometry and solutions. And you can start either from the grams, or you can start from a volume of another solution. And these kinds of calculations are how we can find, say, the concentration of an acid or a base by reacting it with an acid or a base of a solution that we know the concentration of, and we can then find the molarity. So what we're going to do is I'm going to give you, here's the balanced chemical equation. And so that balanced chemical equation, that is an acid-base reaction, acid-base neutralization reaction. HCl is hydrochloric acid, NaOH is a base. And these will come up again later on. Hopefully we'll get to acids and bases before the end of the year. All right, so we've got this acid-base neutralization reaction making sodium chloride and water. And so I've given you that we're going to take 25 milliliters of HCl with a molarity of 0.1234 molar. And this is going to be our given. And it's going to be neutralized by 23.45 milliliters of our sodium hydroxide solution. Now you notice, you know the molarity here. But even though we know the molarity, we're going to still set, where did it go? Still set that up as our wanted. But what we eventually want to get to is the concentration of the sodium hydroxide solution. Now here's what we're going to be doing. Since we have the volume of the solution with the unknown concentration, so that's solution with the unknown concentration, that's our wanted. We need to determine, now what do you need to determine molarity? You need the moles. So this calculation is going to be broken up for you, the moles of the solute. this calculation is going to be broken up for you into 2 steps. And this will be the case on the homework. This will be the case on the test as well. So if you see this two-step problem, it's going to hopefully solidify in your mind what you need to do. Now, step 2, I've given you a little hint on this notes. On the homework and in the test, they're not going to get those notes. But the first thing we want to do is to determine the molarity of the wanted. So that's our wanted. So this is going to be our stoichiometry question. So set yourself up, question mark, moles of the sodium hydroxide. So remember, we're going to stop at moles. So once we get the moles after the mole-to-mole ratio, don't try to go on. You don't need the mass. You don't need anything else about the sodium hydroxide. The moles of the sodium hydroxide, we're going to start with the volume, 25 milliliters of the hydrochloric acid solution. We have the molarity. Molarity was 0.1234 moles of HCl over 1,000 milliliters of HCl. So we cancel out the milliliters. Again, this is going to leave us with moles of HCl. Now, even though it's a 1-to-1 ratio, and that's a nice thing about some of these, neutralization reactions, some of them you're going to have some stoichiometry. So make sure you do the stoichiometry. It's 1 mole of, it looks like a terrible M. Let me redo that. 1 mole of HCl and 1 in the denominator, 1 mole of NaOH. In the numerator, cancel out the moles of HCl. And notice we now have what we're looking for. So stop your calculation here and do the math. And we should get, if that would stay still for me. Okay, let's try that again. Oh, no, I don't want that green mark there. Well, I gave you a little time. Maybe you did the math, maybe you didn't. We're going to get, here we go again, 0.00, watch those zeros, make sure you get them all in there, 3085. I'm using 4 sig figs because I started with 4 sig figs, and if you noticed, I made all of my molarities in 4 sig figs. And so now that's moles of my NaOH. Take a deep breath. We are almost done with today's lesson. Because notice that we have our moles of sodium hydroxide. We've got the volume of the sodium hydroxide right up here. Let me change colors so that I can emphasize what's going on here. Let's use orange. So we're going to look up here and we've got the volume. So now we're going to take both of those down here, and we're going to say the molarity, M, is equal to the 0.003085 moles of NaOH. And we're going to, let's go ahead and put the 23.45. Yeah, I have I don't know, runs on the mind here. 1, 2, 3, 4, 2, 3, 4, 5 milliliters of sodium hydroxide solution, because we can convert that to liters with a little conversion factor here. We can do let's see, we have milliliters up on top. That's 1,000. We have 1 liter in the denominator. The milliliters cancel out, and it's going to leave us with liters, which is what we need for our molarity. And when you do the math, we get 0.1316 molar sodium hydroxide, sodium NaOH. Now, if you did want to do the calculation first to convert to liters first, you could do that, converting to liters first, or milliliters to liters. We have 23.45 milliliters times 1 liter over 1,000 milliliters. Now the milliliters are going to cancel out, and they're going to give us 0.0234 5 liters. Again, notice we went from the 1,000 milliliters down to 1 liter. So the number got divided by 1,000. I hope this is helping you, those of you who've been having difficulty with remembering how to do those conversions. And then we just put this into our equation, into our calculation. The molarity is equal to 0.003085 moles of sodium hydroxide, and divide that by 0.02345 liters of sodium hydroxide, and that's going to give us the same number, 0.1316 molar sodium hydroxide. All right, so this homework is going to be due, when do I have this due? I think it's due on Friday. Let me see, check the schedule. Due 3 p.m. on Friday, May 8th. And then there's going to be no new homework on Friday. Instead, what I want you to do over the weekend is to work on the molarity and absorbance lab so that we can discuss homework 15.3, 15.4, and the lab in class on Monday. All right. Have a wonderful weekend, and I will see you Monday.